Welcome to Mr. Mac's Physics channel. He can explain things really well, and is a lot of fun to watch.
Hi, it's Mr. Mac, and we're going to be learning about dynamics, and in this first part we're looking at forces. So the inquiry question is, how are forces produced between objects, and what effects do forces produce? We're learning to describe static and dynamic interactions between objects due to different forces, and by the end of this we'll be able to solve problems and make quantitative predictions about resultant and component forces. So what is a force? Well, you've probably learnt in science that a force is a push or a pull or a twist. What are some examples of contact forces? Well, there are several examples, such as when you apply a force to an object, normal forces, frictional forces that oppose motion, air resistance, tension is a force in a string, and forces in springs itself are contact forces. What are some examples then of forces that act at a distance? Well, gravitational force is the obvious one. Also, electric force, where we get static electricity, and magnetic force. These are examples of forces that act at a distance. Well, one of the contact forces is called an applied force. What does that mean? An applied force is a force that is applied to an object by a person or another object. For example, if a person is pushing a chair across a room, then there is an applied force acting on the chair. The normal force is the support force exerted upon an object that is in contact with another stable contact. Can we think of an example of a normal force? Well, in fact, if you're sitting down, as I am, then my weight is pushing downwards, but there's a normal force pushing upwards, the chair against me, and they're equal and opposite. This topic is all about dynamics. And what does dynamics mean? Well, Newton's first law of motion is often stated as an object stays at rest and an object in motion stays in motion with the same speed and in the same direction, unless acted upon by an unbalanced force. Dynamics has to do with forces acting on objects. There are two clauses in Newton's first law of motion and a condition. So the two clauses or parts of the statement, one predicts the behaviour of stationary objects and the other predicts the behaviour of moving objects. And this little flow diagram says that when forces are balanced, objects at rest stay at rest. In other words, the velocity is zero and the acceleration is zero. If forces are balanced, and that's the condition, then objects in motion will continue in that velocity and stay in motion at the same speed and the same direction, and their acceleration is also zero. Now here's an animation that shows a horrible situation where a car hits a brick wall and the driver, without wearing a seatbelt, goes over the top. So if the car were to abruptly stop and the seat belts were not being worn, then the passengers in motion would continue in motion, and that's the key to this. Assuming that there's negligible amount of friction between the passengers and the seats, the passengers would likely be propelled from the car and hurled into the air. Once they leave the car, the passengers become projectiles and continue in a projectile-like motion. And perhaps that might convince some of you to the need to wear your seatbelt. Remember, it's the law. That's the law of inertia. Well, here's a restatement of Newton's laws of motion. We've already seen the first one, which is an object will stay at rest or in uniform motion in a straight line unless acted upon by an external force. The second law of motion says the net external force on an object is equal to its mass times its acceleration. This is true for all situations where mass is constant, so it does not apply to a rocket that expels combustion products, thus reducing its mass. Neither does it apply to an object moving at a velocity close to the speed of light. And so here's the rocket, and you can see the mass coming out as thrust and glowing hot gases. The third law of motion says that all forces in the universe occur in equal but oppositely directed pairs. Well, let's have a look at a worked example based on Newton's laws of motion. In this example, a cup is sitting on a table. The forces acting on the cup are the force downwards, acting on the cup due to gravity, and the normal force pushing upwards on the cup. And the question is, what are the force pairs to each of these forces? So firstly, let's look at data, where Fg is the force due to gravity and Fn is the normal force. And we're told that Fg equals the force of the Earth, gravity, on the cup. And the force of Earth on the cup is equal to the negative of the force of the cup on the Earth. And so the force that is normal is the force of the table, or the Earth if you like, on the cup. And so the force of the table on the cup is equal to the negative of the force of the cup on the table. Therefore, the gravitational force, that's the force of the cup on Earth, is the force pair to the gravitational force of the Earth on the cup, according to Newton's third law. And the contact force, the force of the cup on the table, is the force pair to the normal force of the table on the cup. And in our second worked example, we'll have some numbers to work with this time. A car has a mass of 1,800 kilograms, so 1.8 tons, and accelerates from rest to 12 meters per second in 8 seconds in a direction due east. What force is required to accelerate the car? Well, for this we'll use Newton's second law, but first of all let's write down the data. U, the initial velocity, is 0 meters per second. The final velocity is 12 meters per second. The time taken is 8 seconds, and we want to find the acceleration. We also know the mass. We'll look at that in a minute. First of all, let's find the average acceleration. So v minus u on t. Substituting, we have 12 minus 0 on 8, and then calculating, we have 1.5 meters per second squared, and the direction is an easterly direction. We know the mass, we know the acceleration we've just calculated, we want to find the force. So F equals ma. Substituting, we have 1,800 times 1.5 equals 2,700 newtons. And again, this is the force required, 2,700 newtons eastward.